In high school and college, there's a whole lot of trigonometry. Now, you might remember it as a memorization game with all those trig identities and all those trig functions, but do you really know why sine theta over cosine theta is tangent theta? Or how about sine squared theta plus cosine squared theta equals 1? Now, these could become very simple and very easy to remember if you know the origins of trigonometry and if you know how to solve the trig functions geometrically. The rich history of trigonometry starts over 2,000 years ago with the Babylonians. So in about 300 BC, the Babylonian mathematicians actually had a base 60 number system, and the unit that they used were degrees, and specifically we're going to talk about 60 degrees. So let's look at this construction. So CAB is actually called a chord, and we'll get to that in a little bit. So let's look at the main parts of this construction. So point A is the origin. We have X and Y axes going through A. We have the circle, also circle A around with radius AD. We have two line segments, AC and AB, and we have a chord CB. So AC is created from a ray going from A through C, continuing on, and a ray from A through B, continuing on to create these two line segments. Line segments are stopped at the point in which the ray hits the circle. And so if we look at the important part here, which is 60 degrees. So both of these two rays have a 60-degree separation. Why is that important? Well, let's look at the radius. The radius of the circle is 8.71, and the distance between C and B is 8.71. That seems like a coincidence. Well, actually, the distance between the two AB and the radius AD is actually not a coincidence. If we can let's change the radius. Well, if we change the radius, they actually stay the same. Let's change the position. It also stays the same, so nothing ever changes. So we see here the basis from how a chord is constructed. Now that we know what a chord is, let's fast forward a couple hundred years to Hipparchus of Nicaea. He lived from about 180 to 125 BC. He was primarily an astronomer, but he was also a geographer and a mathematician. He adopted the Babylonian use of degree measure in his own work of trigonometry. He was one of the first, if not the first person to create a table of chord measurements for astronomy other than using the celestial sphere, which the Babylonians used to map out stars. Hipparchus actually used his chord tables and chord systems to actually map out the stars. So some say that Apollonius and Archimedes constructed tables and chords before Hipparchus, although no references to it. Using the same tools as Hipparchus and the Babylonians might have used, let's create our trig construction. First thing we need to do is create our axes. So using a straight edge and chalk, I'll create our axes. So first, the y-axis. And now the x-axis. Next thing that we need to create is a semicircle. So I have this tool, and it keeps the origin of the semicircle at the origin of the graph, and this chalk to denote the semicircle. Next, we need to create some angle, alpha, that passes through with a ray through the semicircle. Call it angle alpha. From here we can see that we have the semicircle. We'll call this the unit circle. So the radius of a unit circle is 1. And we're going to call the point in which the ray from the origin created by angle alpha intersect with the unit circle. Right here, we're going to call that point P. Okay, so let's get started with our trig functions. The first two that are the most simple to see are sine and cosine. Sine can be seen as the distance in y from point P to the x-axis. So sine would be the length from point P, and point P is made by angle array from angle alpha that passes through the unit circle. And this line is going to be orthogonal to the x-axis directly up to P. That's sine of alpha. Now it's complementary cosine. It won't be just the change in y, it'll be the change in x. So with the same concept, it'll be an orthogonal line from y directly to point P. And that would be our cosine. Now next, let's see the tangent function. For the tangent function, let's denote first the principal tangent of this construction. So the principal tangent is a line that is orthogonal to the x-axis, but is tangent to the unit circle. And I'll denote that as a dashed line. Now that we have our principal tangent line, we can see what our tangent function will be. And our tangent length is the distance from the x-axis to the point in which the ray that's created by angle alpha meet. So it'd be this point here. So our tangent length will be the distance between the x-axis up to the point created where the principal tangent line and the ray meet. So right here is our tangent line. So let's do their complementary, cotangent. So using the same concept as from sine is to cosine, as sine is the distance in y, and cosine is the distance in x, tangent is the distance in y, now cotangent is the distance in x. So using the same kind of concept as this principal tangent line, let's do one for the upper end of the unit circle. Now cotangent is the distance from the y-axis that is orthogonal to the y-axis directly to the point in which the ray that's created by angle alpha meets those two lines. So it'd be that point here. That'd be our cotangent. Our next two will be our secant function and our cosecant. First off, with our secant function, it's going to be the distance from the origin all the way up to the point in where the ray that's formed by angle alpha and the principal tangent meet. So from distance from here at origin to this point is our secant function. So the distance for cosecant would be from the y-axis, following the tangent that's orthogonal to the y-axis that's tangent to the unit circle, is to where the ray that's created by angle alpha meet. So this distance would be our cosecant. One thing that you can't do with these old constructions that people might have used 2,000 years ago, 1,500 years ago, all the way up to about 80 years ago, or even sooner than that, is that you can draw this and you have to stop there. But with computer programs that we have today, we can actually graph this and see how the points move. We can grab point P and drag it around and see how it changes in each quadrant. Let's shift into computer graphing. Now, this is something that Ptolemy and Hipparchus definitely did not have during their time, but we, as living in the 21st century that has a program such here as GeoGebra, were able to explore trigonometry where they would not be able to. So back when Ptolemy and Pythagoras and they were making these diagrams, these constructions, they would have to do each iteration by hand again and again on chalk, or back then it would be tablets, where they would have to just do one angle alpha, draw out all the lengths, figure them out, and then start again. Instead of here, we can just create a construction and actually drag our construction around to see how each length changes. So let's just review really fast. So from what I did on the chalk, I just translated here onto the GeoGebra. We have our sine length, cosine length, tangent, secant, cosecant, and of course our angle alpha, which has a ray from the origin through the unit circle that we have here, which is at radius 1. And what we can play here is we can play with the actual scaling factor. So the actual uses why we use the unit circle is when you want to do a real life application, not everything is going to be in 1, 2, or 3 feet, 4 feet, 5 feet. You want to do everything in base 1 so you can scale it to whatever size you want. You can use these same skills to understand how tall a building would be if you're set amount of feet away and you know the angle from the base of the building to the top of the building and you know how far away you are. You're able to use all these trig functions and lengths to figure out how tall and how far away you are from the top of the building. Well, let's jump into this really fast. So we are able to understand, as we get a very small alpha, our sine alpha will be very small because the distance from the x-axis up to the point is very small. But as we get larger and larger, we can see as it gets nearing 90 degrees that our length is nearing and finding its limit towards the radius of the circle, which is 1. Let's look at cosine. Cosine is very small here because it's the distance from the y-axis, and it's very small when it's nearing the y-axis. But as we move our angle alpha down closer and closer to the x-axis, we can see that cosine's limit actually goes to 1. Now what's interesting is we've only been talking about what it means to be in the first quadrant. But what if we go to the second quadrant? What changes? Let's see. So now we're at 90 degrees, and let's just jump over. So now we're on the second quadrant. And one thing to notice here is not all things stay positive and negative. This cosine here would not be positive. The cosine length here is in just the distance from the y-axis to the point. But as you can see, if you use actual coordinates, you know everything's positive here. From the x-axis, up from the x-axis in positive y. This is from the y-axis in the positive x. Everything is positive. From the tangent is positive. And from the y-axis is positive going out to cotangent. But when we get over to here, let's see which ones actually switch over to negative. So we can see here that our sine length is still going to be positive because we're still going from the x-axis in the positive direction to the point P. But what is going to turn negative is cosine because it's going from the y-axis in the negative direction x to point P. Before we talk about tangent and cotangent, there's one other simple part of this construction we can add on here, which is still going to be tangent, still be the length, but it's going to be a whole lot easier to understand where it's going to be positive and where it's going to be negative. So we know that the tangent that we defined in our chalkboard construction here on our GeoGebra construction, it is a tangential line that passes through the x-axis as tangent to the unit circle up to the point where the ray that's formed by angle alpha intersect, which would be up here from this point directly down, that's orthogonal to the x-axis. This distance here would be tangent. But another way to construct tangent would be you take point P, a tangential line through point P that's orthogonal to the ray that's formed by angle alpha down to the x-axis. This is also tangent. Similarly, we can think about cotangent. So it's going to be on the same tangential line, but instead of from point P down to the x-axis, it'll be from point P up to the y-axis. Okay, so let's go back to the second quadrant and find out which ones are positive and negative. Now we can see here for tangent and cotangent, we're able to see that in the second quadrant, the x values are negative, and we can tell here that the tangent line has a negative x-axis component from the delta x's from here to here. And similarly with cotangent, we can tell that there's a negative x delta from this point to the y-axis. And let's talk about secant and cosecant. So let's go back to the first quadrant again, and we're going to think about another construction that we can do for cosecant and secant instead of secant being from the origin and following on the same ray that's caused by angle alpha up to the tangent point down. From the distance between these two this intersection down to the origin is our secant line, and our cosecant line is from origin out to the cotangent intersection with that ray caused by angle alpha. Let's see another way we can write that. So another way we can write cosecant is we use the same kind of cotangent idea where it goes from the origin up to cotangent in this intersection. We're going to do the same thing, but from the origin we're going to stay orthogonal to the x-axis on the y-axis up to the point where our new construction of cotangent hits the y-axis. And for our secant, we're going to use the same idea, so let's see that. So it's going to be orthogonal to the y-axis, and it's going to lie on the x-axis from the origin out to the point where our new construction of tangent intersects with the secant line, which would be from this point here to the origin is the distance and length for secant. So let's see what they're going to be positive or negative in the second quadrant. So we're going to move this here, and first we're going to talk about secant. So if we are greater than 90 degrees, and in the second quadrant, we're going to be able to see that secant is going to be negative. So why is this? Because we go from the origin out to the point where tangent hits and intersects with secant. So from this point, this intersection here to the origin is going to be secant. But from here, we start at the origin and go in the negative x direction out to our length, therefore giving it a negative value. So let's look at cosecant. Cosecant is actually going to be positive in the second quadrant because we're able to see that it's orthogonal to the x-axis. So it's going to lie on the y-axis up to the point where our new construction of cotangent intersects with the y-axis, which would be at this point here. And we can see that the component is actually in the positive at y direction. And let's quickly go through the third and fourth quadrants. And in the fourth quadrant, we're going to be able to see that our sine is going to be negative because it's going from the x-axis down in the negative y direction to point P. And cosine is also going to be negative because it's going from the y-axis in the negative x direction to point P. But tangent and cotangent are positive because they have a x and y direction. So both negatives come together to make the positive. So both tangent and cotangent are positive, and both secant and cosecant are negative because it has a negative. Cosecant here has a negative y direction from the origin to the point where cotangent of our new construction meets the y-axis. And for secant, it's in the negative x direction. So we know that sine is negative, cosine is negative, tangent is positive, cotangent is positive, secant and cosecant are both negative. And let's go hit the fourth quadrant. So in the fourth quadrant, we're going to be able to see that sine is negative because we're going from the x-axis that's orthogonal to the x-axis to the point P in the negative y direction. So this sine is going to be negative. Cosine is going to be positive because we're going in the positive x direction from the y-axis. And we're going to see that tangent is negative because there's a negative component to the direction of tangent, which would be our negative y component to our line that's tangent. And cotangent's also going to be negative because it has a negative component in its direction as well. Now secant is positive, and we can see that by our second construction of secant. So we don't pay attention to this secant line, we actually pay attention to our new construction of secant line, which starts at the origin in the positive x direction out to the point where tangent of our new construction of tangent hits the x-axis, and we're able to see that it has a positive x direction, so that secant is positive, and cosecant is negative because of our new construction of cotangent, where it goes from point P as a cotangent down to the y-axis. Cosecant is from origin in the negative y direction to that intersection, so cosecant is negative. Let's talk about some unconventional lengths that we don't talk about in the common vernacular for trigonometry anymore, but here's some interesting lengths that they used maybe in Ptolemy's day. So let's talk about versed sine. So versed sine is the distance from the point in which the sine line intersects with the x-axis out to the point on the unit circle. So it'd be from this distance here to the unit circle, and that's brown. From this point to this point, that's the distance for versed sine. And let's talk about the chord really fast. We talked about earlier, but the chord would be from the point P down to where the unit circle and the x-axis meet. That is the chord length. And we can talk about coversed sine. So coversed sine is the distance if we look at cosine. So it's the distance from where cosine meets the y-axis up to where the unit circle meets the y-axis. So it'd be from the distance from here up to the point where there's an intersection between the unit circle and the y-axis. So let's see that now. So that is in light blue from this point to this point. Now there's an exterior secant, and this is seen only with our second construction of the tangent line that we found. So let me do our tangent sub 1 that we found earlier. So the exterior secant is from the point in which the x-axis and the principal tangent line, that point of intersection, the distance from there out to the tangent where the tangent line meets the x-axis. So from this distance from here to here is our exterior secant, and that's seen here in magenta. So these are some of the uncommon lengths that we don't really use in trigonometry anymore, but it is definitely something to note for, and it's to help deepen your understanding for trigonometry. Primarily in high school, you're told to memorize a trig table like this, but that's just too tedious and long to remember one digit by one digit. But the construction that we created actually tells you how and what the values are for the key angles, such as 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And so let's look at the length really fast. So we know that the cosine is the x component. I'm actually going to move cosine down to the x-axis because we know that the distance from point P to the y-axis is the same as this point down here to the point of origin. So I'm going to move that down. I can see that it explicitly is the x component. And I can see it as a triangle right here. That will be important later. So let's look at 0 degrees. So as we get closer and closer, and the limit is getting closer to 0 degrees, we can notice that tangent and sine are going to 0. Secant is going to 1. And cosine is going to 1. And that makes sense because cosine is the x component, and it's going closer and closer to 0 degrees, and therefore the x component is just becoming the radius. And secant makes sense of going to 1 because secant is the point of origin to the tangent line right here. And we're getting closer and closer. Point P is getting closer to the principal tangent line, therefore secant will go closer into 1. Notice anything else? Let's notice cotangent. Cotangent actually as the angle gets smaller and smaller, cotangent gets larger and larger, and actually the limit goes to infinity, so that it is undefined, because at 0 degrees there are two parallel lines, so it's undefined of length. And so that's for cotangent. And cosecant is the same thing, because cosecant and cotangent are dependent on one another, because cotangent and cosecant, specifically cosecant, is from the origin out to the point of intersection of the cotangent line from the ray caused by angle alpha. So if that's the intersection, and we know that cotangent goes to infinity, we also know that cosecant will go to infinity, and therefore the answers will be undefined. So now we're from 0, let's move our way up to 30 degrees. Now let's work on alpha equals 30 degrees and the trig lengths for those. So if you remember from the trig table, we know that sine of 30 degrees is 1/2 and cosine of 30 degrees is square root of 3/2. Ew, that does not sound nice, that sounds gross. So how do we find that using just our construction that we made? Now we're not going to go figuring out and do so many iterations that we know that square root of 3. No, we're going to use some simple geometric ideas. Specifically, this one we're going to talk about special right triangles. And so this one right here, so if alpha is 30 degrees, we know this is a right angle, so this is 90 degrees. That's 120, and the difference between 120 and 180 is 60, so this is a 30, 60, 90 triangle. So this is a special case. So the side length go as this. So if you have the shortest leg as 1, then the hypotenuse is going to be 2 times that length, and the longer leg that is not hypotenuse is going to be square root of 3. And of course that's a scaling factor, because if this is 1 and this is 2, it'd be 2 times 2, and then this one would be square root of 3 times 2. So how do we go from knowing that this is a special right triangle and finding the side lengths to actually figure out the side length? Well, what do we know? We know that the hypotenuse here is 1. So if we know the hypotenuse here is 1, we know this length right here is 1. And if we know this hypotenuse is 1, that's half of our known value of a 30-60 right triangle, which this should be 2 times our base unit 1, but we know it's 1, so it's 1/2. And so we're going to do the same thing here at the side length, which we know right here should just be our base unit 1, but we know it's 1/2 of that, so we know our sine is going to be 1/2. And for our cosine, it's going to be square root of 3 times our base unit, which we found out is 1/2. So it'll be square root of 3 times 1/2. Therefore, that's how you get sine being 1/2, is because if we know our hypotenuse is 1, but we know our special right triangle uses is going to be 2 times our unit, we know our unit's going to be 1/2 that, and we're going to find that length. So, continuing on, let's figure out what tangent is. So tangent is just using this outer triangle here, using the same concept. And we know here, so we know that tangent of alpha is going to be square root of 3/3. Cosecant of alpha is going to be 2. Secant of alpha is going to be 2 over square root of 3. And cotangent of alpha is going to be square root of 3. And this is all just using the special right triangles. If it's using the triangle from point of origin out and using this triangle, or you know that this triangle here and this triangle here is similar, and therefore this triangle up here are also similar. And before we go to our 45-degree angle, let's talk about alpha being 60 degrees. So we're going to use the exact same special right triangle, but this time our alpha is 60 degrees instead of 30 degrees, so out here is our 30 degrees. So we know this short length here is going to be 1/2 of our scaling factor, and our sine length is going to be the longer leg, not the hypotenuse, which is going to be square root of 3 times our scaling factor. And our hypotenuse, we know it is 1 because it's the radius of the circle, so we know this is still going to be, our scaling factor is going to be 1/2, because this should be 2 times our scaling factor. And if it's 2 times our scaling factor of 1, and we know it's going to be 1, it's going to be 1/2. So if we use our 1/2 idea here, this length here is going to be square root of 3 times our scaling factor of 1/2, and our cosine is going to be our scaling factor as it is. And if we know our scaling factor is 1/2, we can just translate that to the other lengths, such as we know tangent is going to be square root of 3, cosecant is going to be 2 over square root of 3, secant is going to be 2, cotangent is going to be square root of 3 over 3. Now notice that cotangent and tangent flipped from 30 degrees from 60 degrees, and sine and cosine flipped from 30 degrees and 60 degrees. Our last major special angle is 45 degrees. And so this is going to use another special right triangle, the 45-45-90 special right triangle. Now these side lengths go as follows. So if we have two legs at some 1 unit, that means our hypotenuse is the square root of 2 times that scaling factor. So let's think about this. So our hypotenuse is 1 and not square root of 2 times x. So therefore, that's just going to be translated to these side lengths. Now we're going to use that scaling factor to turn this to 1. So that's going to be multiplying both of these side lengths here by square root of 2 over 2. And so that's why the x component, which is cosine, is square root of 2 over 2, which is the exact same as the sine, which is square root of 2 over 2, because the 45-45-90 triangle is an isosceles triangle, whereas both of these legs are the same distance. And we'll use this as a similar triangle. So if we see a triangle here, which is 45-45-90, we can also, this is the same as we see a triangle here from this point here all the way out to where tangent cotangent meet back down to the x-axis. And if we draw a chord between the two, we will see this. We'll be able to see that both side lengths are 1, and this distance will actually be square root of 2. And so the actual values are tangent is 1 and cotangent are 1, as we can see here. Secant is square root of 2, and cosecant is square root of 2 as well. Now the last basic one that we're going to talk about is when alpha is 90 degrees. So this one we're going to use the same concepts as when we found when alpha was 0 degrees. So what are the major functions we're going to be looking at? So let's start with ones that are 0. So we're going to talk about the difference in the x direction, which we know is cosine. So as alpha gets closer and closer to 90 degrees, we notice that cosine is getting closer and closer to 0. And that makes sense because cosine is the difference in the x direction, and it's getting less and less because as alpha goes to 90 degrees, the ray that's caused by angle alpha actually lives on the y-axis. And so if that is true, we know that cotangent, which is the distance from the intersection of the y-axis and the unit circle in the positive y direction, we can tell to the ray caused by angle alpha, we know that it's going to get smaller and smaller because the distance is going to get smaller because the ray is going to live on the y-axis. And we know that sine is going to be 1 because it's the distance from the x-axis up to the point P, and when it gets closer and closer, point P gets the same, becomes the radius of the unit circle, which is 1. And cosecant goes to 1 as well because cosecant is the distance from the origin up to the cotangent line. And so we know that if cotangent goes to 0, we know that all the lengths are going to converge to this point P. Now, what are the undefined lengths when alpha goes to 90 degrees? Well, it's going to be tangent and secant. And let's see it. So as angle increases, we're going to pay attention to tangent here. It's just going to increase and increase because we notice that the ray is getting further and further apart. And when alpha is actually 90 degrees, the ray is parallel to the tangent line. and it makes it undefined with the lengths because they're parallel to each other. And this is the same concept as it is with secant. Because if secant line is the distance from the origin to where the tangent line and the ray meet, that's never going to happen because the tangent line is parallel to the ray caused by angle alpha. So if they'll never meet, it's an undefined length because of the two parallel lines. Okay, so those are the special angles: 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. But what about other quadrants? Let's relate a concept. So earlier I talked about the positive and negative lengths and functions in different quadrants. Well, they're this exact. So all you're going to do is translate those positive and negatives to the values you already know. And it's the same exact special right triangles, and they're the exact same values as before, just with a negative sign in all four quadrants that you've derived the positive and negative in each quadrant as well. Earlier in the video, I was able to show that a trig construction that would be able to form trig functions as length, such as sine and cosine, as the x and y component. Although in a lot of trig problems you come across, they don't just deal with one angle alpha, they deal with multiple angles, and sometimes splitting angles in half. So I'm going to show you how to find higher order trig identities and functions through the use of projections, while using some uses of similarity as well. So we're going to draw an angle alpha that we had before, but this time we're actually going to show an angle beta as well. We're going to say that this angle here is alpha plus beta. Now, how would we be able to find sine of alpha plus beta or cosine of alpha plus beta? We're going to need to use projections. Finding sine of alpha plus beta and cosine alpha plus beta would seem very difficult unless you use projections. So for this construction, we're actually going to use double projections. We're going to do a projection of a projection. And so for this one, we're going to actually do projection of alpha back onto alpha, and we're going to use it by drawing orthogonal lines, which are perpendicular lines. We're going to draw them off of the ray that is formed from angle alpha first. So we're going to find a perpendicular line, so I'm going to use the straight edge to find the perpendicular line down to the ray. And I'm going to do the projection from the point on the unit circle where the ray that's formed by angle alpha plus beta hits the unit circle. And I'm going to project this line down to the x-axis. Okay, so there's one other piece that we need to do, and that's we're going to fill in a similar triangle from here to here. So I'm going to draw a perpendicular line from this line over to the point here. And we're able to see that this angle here is angle alpha because we projected angle alpha from this line down. Before we go any further, let's go ahead and remark some notable lengths. So we're going to mark here, here. And we notice that this line here is congruent to this line. We're going to remark that this line here here. Okay, let's get started with sine of alpha plus beta. So we see that sine of alpha plus beta is equal to the blue line plus the green line. So equal to the blue line plus the green line. Now the problem arises is how we find what each of these lengths are. And so if we think of the similar triangle here that is similar to this triangle here, which is seen as a 90-degree angle here, 90-degree angle here, they both share the angle alpha, therefore they share these two angles here. Now that we know that sine of alpha plus beta is the blue line plus the green line, let's figure out how we can find this green portion right here. And we can see that this green portion right here is congruent to the length of this length right here, which almost looks like it's the sine of alpha, but instead of sine of alpha, which would be right here, it looks like it was scaled down. It actually is scaled down by something. So now that we know that it's going to be sine of alpha, but we know it's going to be scaled down by something, and so we have to find some kind of scaling factor. So the scaling factor is actually seen by a different length here, so it's scaled down to here, which we can follow this up. We actually notice that it's scaled by the cosine of beta. Because the cosine of beta, which would be the x component of the angle beta, which would be from the origin to this point here. And so now that we have the green line here, we just need to add on the blue line. So how do we find the blue line here? So using the same concept that we found that it was the sine of alpha and scaled by cosine beta, we're going to do the same idea and we're going to find some length here, which we see that it is, which now that we see that the cosine of alpha here, instead of cosine alpha here, we're going to look at the cosine of alpha here, is scaled by the sine of beta. We know that the green part is here and the blue part is here. We can now add the two together. So written out, other than denoting the blue line and green line, we're going to substitute those in with those lines. So we're going to see that sine of alpha plus beta equals the sine of alpha that has the scaling factor of cosine beta, which denotes this green line from here to here, is added on to cosine of alpha that has a scaling factor of sine of beta, which is this blue line from here to here. So we learned that earlier part of the video what sine is, and that's just the y component. So for the y component of alpha plus beta would be the green part plus the blue part, which would be the perpendicular line from the x-axis up to the point where alpha plus beta, the ray formed by alpha plus beta, hits the unit circle. And so we found that to be the green line plus the blue line, which is sine alpha that's scaled by cosine beta plus cosine alpha that's scaled by sine of beta, which would be from here to here. Using the same concepts as finding sine of alpha plus beta, let's talk about cosine of alpha plus beta using this construction of double projections. Earlier in the video, we talked about what the cosine length is, and that's the x component. So we're finding the x component of the ray that's formed by angles alpha plus beta, which would be this length here in yellow. So we're trying to find yellow. We find yellow by taking the total length, subtracting this smaller red length. So I'm going to denote this total length here in orange. And we're going to subtract that by this red length here. And that's going to find just what we want, which is this yellow length here. First of all, let's find this orange length here. So this orange length almost looks like it's going to be the cosine of alpha, but not quite, because cosine of alpha would be from origin out to here at this point, which would be the orthogonal line from the x-axis up to the point where the ray that's formed by angle alpha would be hitting the unit circle. But it's not. It's a little bit before. But using the same idea of scaling factors, we're going to start with our cosine of alpha. But we're going to not have it here, but we're going to scale it down. But scale it down to the point here, which is actually the cosine of beta. Okay, so now we have this orange length. Now we need to subtract this red length here because we only want the length here, which is the x component of the ray that's formed by angle alpha and angle beta. And so how do we find this small length here? Well, it looks kind of weird and you might not be able to find it, but we know this length is congruent and the same as this length here. So if we look at this length here, and we know this is angle alpha, this angle alpha has this sine length here. So we're going to subtract this. We know it's going to be some sine length of alpha, but we know this sine length of alpha is way different from the actual sine length of alpha. So we know that we have a scaling factor here too. Now what's the scaling factor here? Let's follow it. So the scaling factor is from here, which would be here, but its scaling factor to what the hypotenuse is. And this hypotenuse is, look at this, the sine of beta. And let's see if this checks out. If we have cosine alpha scaled by cosine beta, and now we're subtracting this, which is this length here, which is sine of alpha scaled by sine of beta. So now we have this length subtracted by this length, and that equals this length here, which is what we want, which is the x component that's formed by the ray caused by angle alpha and angle beta in summation. So let's head over back to technology. So on the chalkboard, we were able to prove the two higher order identities, which is sine alpha plus beta and cosine alpha plus beta. So I was able to make this construction on GeoGebra, and this allows us to use technology unlike a lot of the old mathematicians wouldn't be able to, but we're able to slide around and change the inputs and our alphas and betas. And I was actually made these monitors right here to where I was able to show what each length is, what it is as trig lengths, the actual trig, the actual angle, the actual angles, and the actual length. Now for this construction, I used my radius of my circle being 3 instead of radius 1. So these values will not be exactly what it would be if it was base 1, but it'll be 3 times the amount. And from here you'd be able to set some alpha and set some beta 2 times alpha, and your half angle formulas will be able to be exemplified. So this is how you would find your 2 higher order trig identities that allow you to have your higher order identities such as half angle identities to fall out by using this construction of double projection. This video was produced to show a short history of trigonometry, as well as exemplify 2 constructions of trigonometry to show the lower and higher order trig identities, such as sine alpha plus beta, cosine alpha plus beta, sine squared alpha plus cosine squared alpha equals 1, and many others. This also allows you to show the lengths of special right triangles such as 30, 60, 90 triangles and 45, 45, 90 triangles that is shown as such as sine of 30 degrees, cosine of 30 degrees, cosine of 60 degrees, cosine of 60 degrees. All of this together will allow you to find other trig identities as well as higher order trig identities to be found from sine alpha plus beta and cosine alpha plus beta. These skills will allow you to further your understanding in both geometry, similar triangles, projections, and Pythagorean theorem, while fully understanding where, why, and how you get trig lengths. Thank you.